GEOGADKA. Webinaria.
Today I will try to address problems connected with soil erosion and the impact that humans can have on soil erosion. And I will do it by reviewing some results that together with Matuma we are getting in a project financed by the National Science Center. Before starting, I would just to introduce a bit what I was speaking about. Basically, this is a video, a simple experiment showing what water can do on soil and how the water can mobilize soil. So you have those three bottles on the right hand side. There's a bottle filled with bare sand, just with sand, and in the middle this is another bottle with sand, but at the end, at the outlet, there's some rocks, some small pebbles that can help in slowing down erosion, and then vegetation on the sand. The experiments consist in basically throwing water, putting water on top of the sand and seeing what comes out. And as you can see here, without anything there, if the water or if the precipitation goes over the sand, all the sands come out straight with the water. In the middle, there's another bottle. The process is the same as long as the sand arrives to the outlet. In this outlet, there's a kind of barrier that can entrap sand. So only the clear water goes out. And this last part, there's vegetation, which contributes in fixing the sand, fixing the soil, and in reducing the erosion. So also in this case, only clear water comes out. This can be checked by looking at the water collected out of the bottle. You can see there's dirty sand in the case of sand without any barrier. While in the other two cases, the water is kind of clear. So that's a simple example of what water can do on soil and why soil erosion can be a good topic to be studied. And also, in this sense, there's also something that we will review later about the vegetation cover in this case, or some physical barriers to stop soil erosion in the middle, like in the middle case. So moving on, why we need this kind of studies. So basically, in these slides, I summarize some past studies. In the figure, you can see a study from 2017 about the soil worldwide. In this case, you have regions with stable soil, so no soil erosion basically in green, and then we go towards degraded and very degraded soil in orange and red, and you can see that basically the entire world is more or less subjected to soil erosion, apart from Russia and in Canada, part of the US. In this specific project, we are not looking at the entire world. We are focusing on Ethiopia, which is here, and it's the country, Motuma's country, and it's a country highly affected by soil erosion. As you can see here, there are various studies in Ethiopia. Generally, around 1.5 billion tons of soil are eroded per year, which means around 25 to 30 tons per hectare per year. These numbers seems high, but they are comparable to what happens in Europe. So today I will just show you those examples from Ethiopia, because we investigated this part of the world, but similar situation is also common in Europe. So all those results can be somehow translated also to Europe. So how we perform this study? Basically starting from evaluating what happened in the past. In this case, as said, I'm focused on Ethiopia, which is here in Africa. We investigated a number of studies performed during the last 3 decades about the changes in the use of the land and the type of land coverage. And as you can see in this graph, there's in the last 30 years, there's an increase in areas covered by agricultural fields and a huge increase of areas covered by villages. That's because Ethiopia has an increasing population. So to increase the socioeconomic conditions, well, there's a need to build new houses, to build new villages, and to have more intensive agriculture. Of course, all those things means that the natural vegetation tends to disappear. So we move from kind of vegetated condition to more bare lands. So you can imagine what might happen, reminding what happened in the example with the bottles, going from a situation where the vegetation tends to fix the soil to agricultural field where the soil is easily eroded. To have some better ideas about the impact that humans can have on soil erosion, on the soil loss, we analyze the Fincha basin. The Fincha basin is a basin in the middle of Ethiopia, around 300 kilometers from the capital, Addis Ababa, and is one of the basins that gives water to the Blue Nile basin and then to the Nile. In this case, as you can see here in this elevation map, there's the slope varies across the basin, and the elevation goes from around 3,000 meters above sea level to 800 meters. So there's all those agricultural fields that were constructed are not flat, but there's some kind of slope. In terms of hydrological conditions, well, basically we can characterize the basin with 4 main seasons. The summer, which is characterized by heavy rainfalls. Then the harvest season from September to November. And the winter is the most dry season where there's basically no rain. And then the spring where the rains are just happening sometimes, and is the hottest season. So as you can see from the numbers reported here, the annual rainfall spans from 1.3 to 1.8 meter per year, but all this rainfall basically falls just in summer, which has so all the precipitation happens in just in 3 months. So it's like throwing water directly on dry soil. So this means that the rainfall mobilizes soils rather fast, because there's no possibility for the water to infiltrate in the soil, as the soil is already dry. As you can see here, most of the rainfall is concentrated in the southern and western highlands, so it's the precipitation is not uniform across the basin, despite the basin is rather small. So how to answer to the question about the connection between land use and the soil erosion? So basically, first we investigated the land use, and we made that at the basin scale. For doing at the basin scale, we need some information largely, that can represent large watersheds. So the obvious option is to go for satellite images. In this case, we use Landsat images, which have a spatial resolution of 30 meters. And as you can see in this graph, we had to combine multiple data sets because different Landsat missions were sent to the space a long time. We combined also images coming from different dates. It's reported here in terms of path and rows, because the basin is larger than the actual images. So we had to consider different dates and different images, and we combined those images. All these images refer to dry conditions. As you can see here, they were acquired in January, so it's the dry condition. And then we analyze past changes, looking at three different reference years: 89, 2004, and 2019. In this case, 2019 is considered the actual date. So we classify the images based on those satellite information, and then we validate our classification using field surveys, so field information, photos, and also interview made with the local population. Also to have a better idea about what was the land use in the past, and if what we derived from the satellite images was okay, also looking at the past. So then we got these three beautiful, colorful maps. In this case, what is reported is the classification in terms of 6 land use classes. Spans from water body, which is the blue part, to forest and grass. So dark green is forest and light green is grass, and built up areas is red, and shrubs is this part in the northern part, while the yellow part is the agricultural field. So going from 89 to 2019, you can see that reasonable increase in yellow areas and a decrease in dark red. This means that we have an increase in areas covered by human-created agricultural fields, and we have a decrease of natural forest. What is also important here, if you look at the water bodies, in this case, you can see this big lake, which is created by the Fincha River and the Fincha Dam here, and then here one small lake. All those lakes are were created by building dams at the outlet here and there. And if you go from 2004 to 2019, you can see that another water bodies appears. That's because another dam was built. So this water bodies was created to collect. All those water bodies were created to collect rain, as it happens only once in a while during the year, and also to create hydropower energy for agricultural use, for potable use. So all those reservoirs are multi-purpose reservoirs. And as you might imagine, building new reservoirs means that population tends to move close to the reservoir because it's easier to cultivate areas there. So there's also a huge component of internal displacement because the construction of new reservoirs, the creation of new agricultural field for cultivating sugarcane for sugar factories, which is a major industry in this basin. So we can compare those maps looking at the colors, or we can compare it looking at the areas covered by the different land classes. Here, just important three comparison between the 3 different years. But what is important to notice is that the trend between 89 and 2019 is that agricultural areas covered by agricultural fields, water bodies, and build-up areas are decreasing over time. We have a net increase of those areas, and of course we have also a decrease in terms of forest, grass, and shrubs. So the man-made areas are increasing, the natural areas are decreasing over time. So this means that we observe rather relevant changes in land use. Then we use this information also to somehow characterize what might be the future. So we use some numerical approaches to forecast future conditions, assuming that what we observe in the past will remain the same also in the future. So this might involve some uncertainties, as you can imagine, because we assume that no new dams will be built, no significant displacement will happen, and all those things. So basically, we came out with 3 different maps also for the future in 2030, 40, and 50, and you can see that the trend is the same. So in 30 years, we should expect areas, well, a basin mostly covered by agriculture and grass areas, with rather big villages. And this means that we also have a net decrease of areas covered by natural forests. Therefore, a decrease in environmental values in ecosystem services, and also a decrease in areas covered by vegetation, so a decrease of areas covered fixed by the vegetation. So we might expect also an increase in soil loss. So what we observe here, what we summarize here, is the evolution over the entire observed period. So three decades in the past, 3 decades in the future. And those are the numbers in terms of variation of hectares between the various periods and in percentage. Basically, if the conclusion is the same, we have an increase in agricultural, build-up areas and water bodies, and we have a significant decrease in forests and shrubs. This means that we have a decrease in all those areas which are fixed by vegetation. So this means that also we observe, and we will observe, rather significant impact of humans on the land use. How to answer to this question about increasing soil loss? So we use a mathematical model to simulate the sediments detached from the basin, from the hillslopes, and moving towards the Fincha dam outlet, which is the dam that stops basically the Fincha River, which was this big river in the middle of the basin. We selected this outlet because there are some information about the water flow and sediments at the outlet of the dam, so we were able to calibrate the model. What we observe looking at this graph, basically, if we look at the past in the 89, we can see that we speak about 1.5 million tons per year of sediment arriving to the dam. Then over time, we have an increase in sediments entering the dam, meaning that we have an increase in sediments in soil detached from the hillslopes. So it's worth to remind that all those, this trend is basically derived from changing land use. So basically, we can answer to this question here: if the humans are humans changing land use, increasing soil loss? Yes, they are, and all this increase in soil loss has multiple consequences. In this case, if we just focus on the dam, more sediments means that a decrease in water quality and a decrease also in the volume available for water. So this lake will decrease its volume over time because of more soil entering the lake. So all the benefits connected to the volume of the water will decrease, like the hydropower, electricity. Producing the same hydropower electricity needs more time. The water available for agriculture will decrease, and the same for the other uses of this area. And here there are just a couple of images of this soil erosion that happens across Ethiopian hillslopes. In this case, the Fincha, and you can see that the vegetation is pretty low or absent. The sediments will move along the hillslopes with the first flooding event, with the first precipitation. That's the situation. What we can do? Well, basically there are a number of management practices that could be implemented to reduce this erosion. We tested 4 different strategies, which are summarized here. Basically, the contour practice means that plants are planted across the slope contours. In this case, the plants tend to create some kind of water breaks, so the water has more time to infiltrate in the soil, and as long as the water infiltrates the soil, that means that the soil is not detached from the hillslopes and moved downstream. There's also the possibility of creating filter strips, which are large grass strips, created on cultivated areas. They act more or less like contours, so those are kind of barriers that facilitate the water infiltration. And then there is the opportunity to create soil or stone mounds. Basically, those are physical barriers. So elevated soil store barriers that are built along the slope contours and are kind of similar of what you saw in the first video in the middle and the bottle in the middle. And those barriers tends to reduce the flow velocity and runoff. So also in this case, basically the idea is to stop water, and stop the water, the turbid water, the water with sediment to move downstream. And that also the opportunity to create terrassment, basically these new channels which are created across the slopes. In this case, they act like a stone bound, so the water flow velocity is reduced, so the overall erosion is reduced. So also in this case, we can implement those methods in numerical models and obtain some results, which are kind of summarized here. In this case, we investigated the impact of those management practices at the sub-watershed scale. So the idea was to divide the entire Fincha watershed in small sub-watersheds and then see what happens at the local scale. The colors, we go from brown color where we have kind of reduced soil erosion, meaning that the soil erosion is below 11 tons per hectare per year, which is rather acceptable threshold in Ethiopia, to blue colors where we have very huge erosion. So in 2019, this is the situation that we simulated, and applying the different methods, you can see that we actually reduce the soil erosion. And in this case, in 2019, the most efficient method is terracing, where we have more or less all the sub-watershed which are below the critical threshold. If we use, if you look at 2050, so a baseline condition which is characterized by increasing soil erosion, so more worse condition already in the baseline condition, the methods are effective in reducing soil erosion, but are not that effective in reducing it below the critical threshold. Also, the terracing, you can see there are some green and yellow areas, which are which means that soil erosion those sub-watershed is still really important. So this gives us some indication about what can be done and what are also, but also what are the limitations of our approach. So basically, what can be done is to investigate a series of management practices to see what happens in terms of sediment yield and what are the most efficient practices at the watershed and sub-watershed scale. Because looking at the sub-watershed scale, as you can see, there are differences between the different sub-watersheds because the methods depend on the local characteristics. And at the watershed scale, so for the entire Fincha watershed, we can see that there are some methods that perform better than others. In this case, the terracing is performing better than all the other methods for all the years here. Then, moving towards the conclusion of today's speech. So basically, I reported here the example of the Fincha watershed to speak about the impact of land use, of human-driven land use on soil erosion, because this is a watershed which is highly treated by soil erosion and is a watershed which economy is fully or largely based on agriculture. So in this case, soil loss plays a major role in the local socioeconomy. We look at the past condition, we observe this erosion, we try to simulate for the future, and well, the trend is more or less the same, especially if no countermeasures will be implemented. In this case, countermeasures are all considering both physical, so implementing some management strategies, but also political changes in the overall management of the basin. The example that about the use of management practices to reduce soil erosion is evident. It was supported, and we can say that the terracing is the most effective management practice to reduce the sediment yield at the watershed scale, and also the subwatershed scale in the majority of the subwatersheds. Then it's needed to investigate more in detail subwatershed per subwatershed to evaluate what management practice, what is the best management practice. Well, those management practices are okay in reducing sediment yield at the watershed scale, but might be not that effective to reduce the soil erosion below the critical threshold, especially in highly impacted areas or in areas which are characterized by high socioeconomic value. This critical threshold, as said, is around 11 tons per hectare per year in Ethiopia, but as you can see, for the future, the majority of those subwatersheds are really not below this critical threshold. Then it's important to remind that we are speaking about a country where the resources are kind of limited, so it's not always possible to implement all the management practices in all the subwatersheds. So it should be considered that we have to prioritize some actions. For example, we need to first study the different management practices and where they might be more effective to prioritize these areas, those soil erosion hotspots, to implement very specific management practices. But this might be done, this can be done only by having reliable data, which is also a major challenge in this case. So for the future, the recommendation that we have is that we have to first start improving the monitoring and the management of those monitoring data, also by improving the technical skills of all the people involved in the monitoring. Then once the hotspots are, when we have a better idea about what are the hotspots, then we can move to implement these management practices, starting from the most effective, of course. And these management practices can be applied also in combination with other management measures. I say both physical and political measures. For example, some ecological measures along the rivers and floodplains for the creation of some buffer. So that was the idea of the study, and this study, as said, was used as an example to investigate how humans can change the land use and how these changes in the land use can change the soil erosion and increase the soil loss. This, as said, is some results from a project financed by the National Science Center of Poland. In the website of the project there are more information, and I'm here to answer your question if any. Thank you.
Projekt GEOGADKA – Geofizyka dla każdego jest współfinansowany ze środków Ministerstwa Edukacji i Nauki w ramach programu Społeczna Odpowiedzialność Nauki.